Hello, this is Johnson Pariki from Aeronautical Engineering. The topic is about the structure of shock waves in binary gas mixtures. Coming to the agenda, we're going to discuss about the introduction of the topic, the shock wave structure, and molecular collisions and their applications. So let's look at into the introduction part. Normal shock waves are an important phenomena in fluid dynamics, occurring when a supersonic flow is abruptly slowed down to subsonic speeds. In binary gas mixtures, such as air, the structure of these shock waves can be quite complex. The behavior of gas mixtures is governed when the law of, by the law of thermodynamics, which dictate dictate how the pressure, temperature, and density of the gases change as they pass through the shock waves. Coming to the shock wave structure, the image which is shown in the left side of the slide is the structure of the shock wave. So at the core level, uh, the circular the circular body, which is in orange color, surrounding with white and by the yellow surrounding layers, is the origin of the shock wave. So the shock wave which is originated at that point is being disputed is being distributed to the other stages, such as we can able to see the blue layer as well as the green layer. So the green layer is the outermost layer of the shock wave. So coming to the topic, in binary gas mixtures, the structure of normal shock wave is determined by the ratio of specific heats of the two gases. This ratio this ratio known as gamma affects how the pressure, temperature, and the density of the gases change across the shock wave. For example, if gamma is less than 1, the shock wave will be weaker and more diffuse, with a longer transition region between the supersonic and the subsonic regions. So this is the structure of the wave structure of the shock wave. Coming to the molecular collision, another factor that affects the structure of a shock wave in a binary gas mixture is the rate of molecular collision between the two gases. When the gases collide, they exchange energy and momentum, which can affect the behavior of the shock wave. In general, the more collisions there are between two gases, the more gradual the shock wave will be. So, this is because the collisions help to dissipate the energy of supersonic gas, slowing it down more gradually as it enters the subsonic region. So, uh, coming to the molecular collisions of the shock wave. So, when the mixture of gas is present at the point of formation of shock, so the molecular level uh, study will be involved in order to identify the effects of the shock wave and the characteristics of the shock wave. So, the molecules of the different gases will be collided each other. As an effect, the momentum of the molecules as well as the energy of the molecules uh, will be changed. The energy will be dissipated in the form of shock gas, wave gas, as well as the as the molecules collided each other, the momentum of the molecules will be increased. So that is a good factor. The increase in the momentum of the molecules is a good factor for the shock wave to study, and that will slow down the free stream velocity at the shock region to supersonic speeds, from supersonic speeds to the subsonic speeds. And moving to the applications of the shock waves. So the study of shock waves in binary gas mixtures has numerous practical applications ranging from aerospace engineering to planetary science. For example, researchers can use their knowledge of shock wave behavior to design more efficient supersonic engines for aircraft, or to model the behavior of shock waves in the atmosphere of other planets such as Mars or Venus. So, the applications of the study of shock waves in binary gas mixtures is numerical practical applications. So, that is, the applications are ranging from aerospace engineering to the planetary science also. As we have discussed about the example, researchers can use their knowledge of shock wave behavior to design more efficient supersonic engines for aircrafts. So, the study of shock waves of binary mixtures, shock waves in the binary gas mixtures. So, they'll help the researchers to gain knowledge about the shockwave behavior, and that knowledge, by the use of that knowledge, they can be able to design more efficient supersonic engines for aircrafts. So to model the behavior of shockwaves in the atmospheres of other planets. So, as we all know, every planet in our solar system consists of different gases, different gas compositions. So, studying the studying the free stream velocity uh, of shock waves is not an accurate study, and uh, is not an deep study for the design of engines for the aircraft. That may be considered only in the atmosphere, but whereas the shock waves shock waves in binary gas mixtures, so these type of studies will be applicable for the uh, interplanetary missions also. So if we consider Mars, for instance Venus are example, the atmosphere, the atmospheric conditions the gas is present are quite different compared to the earth. So in order to make an aircraft to fly in the Martian atmosphere or Venus atmosphere, we need to study the effect of the mixture of gases as well as the temperature effects, pressure effects, all these effects. So what they'll do the most on the performance of the aircraft, performance of the engine and structure of the aircraft. So these studies will allow the researchers to design and uh, efficient supersonic engines of aircrafts for aircrafts. So, for the obvious reasons, we the study of shock waves in binary gas mixtures is more important. I conclude this the presentation with this, and I thank you.